Chapter 3, Section 2, Rolle's Theorem and the Mean Value Theorem. These are two pretty important theorems that you're going to most likely see again. More possible the mean value theorem than Rolle's theorem, but you could see again on the AP test. All right, it says in the last section we studied the extreme value theorem. The extreme value theorem said if you have a continuous function on a closed interval, you're guaranteed absolute extrema on the enclosed interval. But these could occur at the endpoints. These values could occur at the endpoints, and they did in many cases with the examples that I showed in the last video. However, it was a mathematician by the name of Michel Rolle, or Michael Rolle, depending on how you want to pronounce it, who lived way back in the 16 and 1700s, who published a theorem. Oh, I have in 1961. That's a trick. How about 1691? All right. Keep you on your toes there. That published a theorem in 1691 that said under certain conditions you could guarantee the existence of an extreme value in the interior of a closed interval. Notice it does not have to occur at or possibly occur at an endpoint. It's guaranteed that it would be in the interior. Now, what's kind of interesting about this is that Rolle, who was a fairly famous mathematician at the time, did not trust the work of Newton and Leibniz. He didn't trust calculus, and as it turns out, his theorem is probably one of the most fundamental theorems, and of which other topics are built off of in all of calculus. So it's kind of ironic he didn't trust it, but at the same time a very important theorem in calculus. And Rolle's theorem says let f be continuous on AB and be differentiable the closed interval AB and be differentiable on the open interval AB. Now notice here, you have to have both of those conditions met. It has to be continuous and differentiable. If f of A equals f of B, so at the endpoints you have the same y values. At x equal A, x equal B, f of A is equal to f of B. Then there exists at least one number C in the interior such that f prime of C is equal to 0. Now I'm hoping that you can kind of see that with my diagram a little bit here. I have a continuous function on closed interval from A to B, and not only is this continuous, it's differentiable. As far as drawing, I could draw unique tangent lines at any point on this curve. So what I'm saying here is that there's got to be at least one value, at least one, it could be more than one, at least one value C such that the derivative of the function at x equals C is equal to 0, which would mean I would have to be guaranteed one horizontal tangent. There he is. So this would be, and it's not, I mean, the way I drew it, it looks like it's at the midpoint of the interval from A to B, but this has to be at some value C. My curve could look something like this, perhaps. And then I might have more than one value in which f of C, f prime of C is equal to 0. Then I would have a horizontal tangent. So I double dog dare you to try to draw a continuous differentiable function, no corner points, no cusp, between 2 points whose f of A is equal to f of B that doesn't have at least one horizontal tangent line. Here's a function, f of x is equal to x squared minus 6x plus 5. We're to find all values of C in the interval from 2 to 4 such that f prime of C is equal to 0. Well, to see if Rolle's theorem even applies, first I noticed that f is a polynomial. Therefore, f is continuous and differentiable. Just going to abbreviate here a little bit. If I plug in 2 and 4, f of 2, which is 2 squared minus 6 times 2 plus 5, this would be 4 minus 12 would be negative 8 plus 5 is negative 3. F of 4 would be 4 squared minus 6 times 4 plus 5. So that's 16 minus 24 is negative 8 plus 5 is negative 3. Notice here, f of 2 equals f of 4. Therefore, Rolle's theorem applies. Okay, I did all that work just to see if I could even apply Rolle's theorem here. Now, it wants us to find all values of c. So of course I didn't leave myself enough space. I'm going to take the derivative. F prime of x is equal to 2x minus 6. That means f prime of c would be 2c minus 6. I'm going to set that equal to 0. I'm going to solve for c, and I'm going to get c equals 3. Now notice 3 is in the interior. It turns out it's the midpoint, but that's a coincidence. C is in the interior. Rolle's theorem applies. Therefore, find all values of c. C equals 3. Okay? Now, I kind of went into the next part here, but we can use Rolle's theorem to develop the mean value theorem. In fact, it's a key part of the proof of the mean value theorem. The mean value theorem was proven by Joseph Lagrange, or Lagrange. I like Lagrange because of the song by ZZ Top. The mean value theorem kind of goes an extra step. Whereas we have the criteria here that f of a has to equal f of b for us to get this kind of horizontal tangent. Well, what if we don't have f of a equal to f of b? Could we still possibly determine something about maybe a point in the interior of the function? So what the mean value theorem says is that if f is continuous on the closed interval ab and differentiable on the open interval ab, the same as the beginning of Rolle's theorem, right? The same part, same criteria. But this time it says there exists a value c in the open interval, in the interior, in the open interval AB, such that f prime of c is equal to f of b minus f of a over b minus a. Well, f of b minus f of a over b minus a, that's the slope of the secant line through the endpoints. The difference in the y's over the difference in the x's. So what this is saying, and I'm going to try to make a sketch here, because, well, actually I have a sketch coming up here. Let me just kind of show it to you. Here are the endpoints from A to B. This line right here is referred to as the secant line, and its slope would be slope of the secant line. Let's do it this way. F of b minus f of a all over b minus a. Oops, don't need the parenthesis there. So what I'm trying to show here is that there's going to be at least one value c where the derivative at that value is equal to the slope of the secant line. So that means the slope of the tangent line, f prime of c, has to equal the slope of the secant line. Well, hopefully with my diagram, even though my orange line got carried away there a little bit, I'm hoping that you can see that I've got this drawn in such a way that these lines appear to be parallel, that they would have the same slope. Okay. Now, the mean value theorem can be used, not so much Rolle's theorem, but the mean value theorem can be used directly in problem solving. It's been used, the mean value theorem has been used to prove a ton, part of the proof in other theorems. Considered one of the most important theorems in calculus. Well, Rolle's theorem is as well, because Rolle's theorem led to the mean value theorem. And geometrically, and that's what I was trying to show you with my diagram, the mean value theorem guarantees the existence of a tangent line that's parallel to the secant line. At least one. Okay? So let's go back to this diagram here. Slope of the secant line, slope of the tangent line. Now, to use either Rolle's theorem or the mean value theorem, we have to make sure that it satisfies all the criteria. So in this first example here, it says, show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval from 0 to 2. Then find a solution c to the equation f prime of c is equal to f of b minus f of a all over b minus a. Very simple example, very simple function. It's a continuous function. It's differentiable because it's a polynomial. So since f is a polynomial function, it is continuous on 0, 2, and differentiable on the open interval from 0 to 2. Then, therefore, the mean value theorem, which sometimes I just abbreviate MVT, not quite MVT, applies. Okay, now to find that value c, I have to take the derivative. The derivative of f of x is equal to 2x. So f prime of c, that would be 2c, is equal to f of b. This would be f of 2 minus f of 0 all over 2 minus 0. So I get 2c. F of 2 is 4 minus 0 over 2 is 2. Well, c is equal to 1. Now I know for the last couple of examples, my value of c turned out to be the midpoint. That's not always the case. It just happens to be the nice simple examples that I have for you here. So it says find a solution c to which the equation is true, c equals 1. But notice all this had to be stated to kind of back up the fact that I could use the mean value theorem to find that value, value of c. All right, next example. F of x is equal to the square root of 1 minus x squared. A is the point -1, f of -1. B is the point 1, f of 1. We're to find a tangent line to the graph of f in the open interval from -1, 1 that is parallel to the secant here at the secant line AB. Well, it's kind of stepping around it, but this is just saying use the mean value theorem. Now this particular function is going to be okay between -1 and 1 because this graph, it's like a semicircle. Well, I'm going to try to draw a semicircle where this is 1 and this is 1 and this is -1. So this is continuous and differentiable, no problem. So I need to take the derivative. That'll be the challenge here because it's a composite function. So f prime of x is equal to, now this again, think of this as a power with a rational exponent here, the square root. So this would be 1/2 times 1 minus x squared to the -1/2 times -2x, using the chain rule. So this 2 and this 2 cancel, and I end up with the opposite of x all over the square root of 1 minus x squared. And I'm going to set this equal to the slope of the secant line, because that's going to give me the slope of the tangent line. So in this case, the slope, that would be f of 1 minus f of -1 all over 1 minus -1. F of 1 is 0. F of -1 is 0 all over 2. Well, the y values are the same at the end point, so this is actually Rolle's theorem that I'm using. And this is going to equal 0 when the numerator equals 0. So the numerator is equal to 0 when x is 0. And again, I know, it's right in the middle, just a coincidence, but that's the value they're looking for here. Now find a tangent to f. Oh, hang on a second, find a tangent to f. So they actually want the tangent line, find a tangent to f. So x equals 0 is where it occurs at, so that would be at 0, 1, and it's going to be horizontal. So it's going to be the tangent line is y equals 1. Got to make sure I answer what it's asking. It says we can also think of the difference quotient there, f of b minus f of a over b minus a, as the average change. So what the mean value theorem is saying, that the instantaneous change, that's an e there, that's hard to tell, that's a g there, that the instantaneous change at some interval point must be equal to the average change over the entire interval. Now I've talked about this before in a previous section. If you're driving from here to, let's say, someplace 200 miles away and you travel in 4 hours, okay, you're averaging 50 miles an hour. 200 miles divided by 4. You're averaging 50 miles an hour. What the mean value theorem is saying is that somewhere your instantaneous velocity has to be the same as your average velocity. So here's an example. If a car accelerating from 0 to 8 seconds can go 352 feet, its average velocity for the 8-second interval is 44 feet per second, or about 30 miles an hour. This means at some point during the acceleration, the speedometer must be at exactly 30 miles an hour. You have to have the average and the instantaneous occur for some value. That's what this is saying, because this is an average change. Now, Why doesn't the mean value theorem apply for the following problem? On the closed interval from 0 to 6, for f of x equals 2 over x minus 3. Now, at first appearance, you got a closed interval. It's looking good. You got a nice little rational function. But notice that I'm going to have for this rational function a vertical asymptote at x equals 3, which is in the interior here. So this is not continuous. F is not a continuous function. That's why we always check to see if it's continuous and differentiable before we actually apply it. Okay, since I worked at a truck stop when I was 15, now here's a trucker problem. All right, a trucker handed in a ticket at a toll booth showing that in 2 hours she had covered, gosh, my handwriting is bad, 159 miles on a toll road with a speed limit of 65 miles per hour. So 2 hours, she went 159 miles, and the speed limit 65 miles per hour. And the trucker was cited for speeding. So the guy at the toll booth says, hey, buddy, you're getting a ticket. Well, why does she get a ticket? All right, well, the average velocity here is going to be 159 divided by 2, which is 79.5 miles per hour. Well, based on what we were just saying with the mean value theorem, if that's the average that she traveled, somewhere between one toll booth to the next toll booth over that 159-mile trek, she averaged 79.5 miles per hour. Probably did more than just hit it one time, probably going pretty fast for a while. The speed limit is 65, so she receives a ticket. Due to the mean value theorem, which states she was traveling at least she was traveling at least, no, that doesn't sound right either. She was traveling at 79.5 miles per hour at least one instant of the 2 hours. Oh, that is terrible. She receives a ticket due to the mean value theorem, which states that she was traveling at least, I think I should have had the two at-ats. She had at least 79.5 miles per hour at least one time during the 2 hours that she traveled. Hopefully you can state your answers in words a little bit better than I did, and hopefully, again, you can make that a little bit more legible. But the mean value theorem and the Rolle's theorem, definitely put that to memory.